Here on our improper integrals day one notes. So improper integrals are going to be integrals that involve either infinity or negative infinity on our bounds. They also could include, like if we're just going to, if it's from like a vertical asymptote all the way out to another point as well. So it's not necessarily just infinity. So those are what improper integrals are. It's just integrals that either go out to infinity, they involve asymptotes, especially vertical asymptotes, or it's not really common and it's really kind of hard to take the integrals. So what's going to end up happening here is these improper integrals can be evaluated through the definitions listed below, which are all right here. If the limit exists, then it's said to converge. So if the limit exists, then we can actually find the area or whatever the integral is asking for. If it does not exist, then it diverges. So real quick example for you would be, I'll do this in purple. Like if I'm trying to find, let's write it right here in this little corner. Trying to find integral from 0 to infinity of x dx. I'll give a quick little sketch about that. Here's x from 0 going on, and I'm finding all the area from 0 to infinity. Well, it keeps getting bigger and bigger and bigger and bigger, right? So what's going to end up happening here is this is going to not converge. The limit is not going to exist. So this we cannot do. So this would be an example of the limit not existing. And then this would be, this diverges. Okay? Because the area is going to keep adding up, and there's nothing we can do about it. Whereas if we get an example, and this will kind of talk about number one, if we get an example where it starts to decrease like this from 0 to infinity of this function, well, it's decreasing enough, and it's eventually going to converge. All right. So let's go ahead and tackle our first example right here, and then I'll kind of walk you through what we do for these. So first things first is we're not allowed to integrate to infinity. So we need to replace the infinity with the letter. Now, typically, if you look over here, it goes from A to B. I typically, if the top one's infinity, I let B equal infinity. If the bottom one is negative infinity, I let A equal negative infinity. Okay, so in this case, I'm going to integrate from 1 to B of 1 over x dx. Now, since I'm finding B, I'm actually finding the limit as B approaches infinity. So first step is replace that infinity with the letter B. And let's find the limit as we go out to infinity of that b, and then we're just going to go ahead and integrate, and at the very end we do our little limit problem. Okay, so let's do it. So what's the antiderivative of 1 over x times dx? It is indeed ln of x. So let's go ahead and ln of x, evaluate that from 1 to b. Again, this is use our limit notation here. If you leave off your limit notation, you're not going to get credit. So this is going to be the limit as b approaches infinity of ln of b minus ln of 1. So now I'm going to get ln of b. Well, as ln approaches infinity, that's what it looks like, by the way, it's going to keep going up and up and up to infinity. So what's going to happen here? Well, we're going to end up getting infinity minus 0 because ln of 1 is 0. So we're going to get infinity. So this answer diverges. So actually, I cannot find this integral. Again, integrals represent area, so I cannot find the area from 1 to infinity of 1 over x. Okay? So I drew something that looked like it was similar to this right here, but not always the case, because I know 1 over x does decrease. So just be careful. It does not always work like that, and then we will get to examples where they do work, and I'll sketch them out for you so that you know what they look like as well. Okay, so this one diverges. Let's get to our next example here. So 1 to infinity of e to the negative x. So let's replace that infinity with a b. So 1 to b, limit as b approaches infinity, e to the negative x dx. And now I can go ahead and find the antiderivative. This is just kind of like a baby u sub here. So I'm going to get negative e to the negative x. That's my antiderivative of e to the negative x from 1 to b. Limit as b approaches infinity. So I'm going to get the limit as b approaches infinity of negative e to the negative b minus negative e to the negative 1. Let's put these in parentheses. So let's do this piece by piece. What is negative e to the negative b? If you go out to infinity, it's going to keep getting smaller and smaller and smaller, right? So this is actually going to end up equaling 0. So I'm going to get 0 plus 1 over e, because that's what that is. So the answer is just going to be 1 over e. So this one does converge. So what does this one look like? Well, e to the negative x, or just to sketch it out, it's actually exponential. And this just happens to be going this way. Okay. So it would be this area from 1 all the way down to infinity. And this one happens to converge. And that area would just be 1 over e. All right, similar example over here. But this time I'm going to go from negative infinity to 0. So, well, let's make that a to 0. E to the x over 4 dx. And don't forget, this is my limit as a approaches negative infinity. Here's my setup. After you set it up, it's not so bad. Again, just be aware of the baby u sub here. This is going to give me, and you know what? Let's just pretend that we don't do the baby u sub. Just pretend. All right. So let u equal x over 4. Let du equal 1/4 dx. 4 du's equals dx. And let's go ahead and do our u of a is going to be a over 4. And u of 0 is still equal to 0. So using my u sub here, I'm going to get the limit as a approaches negative infinity of my lower limit, which was a, is now a over 4. My upper limit, which is now 0. And this is going to be 4 du, so it's going to be 4 e to the u du. So you can use u sub with improper integrals. So now I don't need to convert anything back. I can just take the antiderivative, which the antiderivative of 4e to the u is just going to be 4 e to the u evaluated from a over 4 to 0. Do not forget this limit notation. So I'm going to end up getting the limit as a approaches negative infinity of, I'm going to pull that 4 out, e to the 0 minus e to the a over 4. Well, what's happening here with as we go out to negative infinity? So helpful to know, again, what e looks like. So e to the a over 4, well, that's positive, so it is in this direction right here. Just since it's 1/4, it's just very slow. And we're going to have an asymptote right here. So what's happening as I go out to negative infinity? It's getting closer and closer to 0. So essentially this right here is going to equal 0. So I'm going to get 4 times 1 minus 0, which is just 4. Okay. So we do need to be sharp on our limits. All right, last example. This is a word problem we have not tackled yet. It has to deal with rotation. I'll just talk about that real quick. That's not the important part of today. The important part is getting through the improper integral part. So let f of x equal e to the negative x, and let r be the region, the first quadrant between the graph of f and the x-axis. Find the volume of the solid generated when r is revolved around the x-axis. So essentially, we're going to be taking this function, and I'm going to sketch it. In the first quadrant, so I'll just sketch this, the first quadrant part. So it looks like this. And I'm going to take all of this green area, and I'm going to revolve it around the x-axis, okay? So it's going to be generated, and it's going to make a shape. It's going to make a shape that's going to end up looking like something like this. Pretend this is 3D. Just do your best 3D pretending. Okay, so this is a 3D figure that just got rotated around. So let's go ahead and talk about how to do this problem. Well, let's set it up. So first off, this is going to turn into some type of circular figure. So area is equal to pi r squared. Okay, volume when you rotate it is going to be pi integrate from a to b of r of x squared dx. Why is this volume? Well, it's just like this pi r squared, except we're adding this extra dimension from a to b and whatever the function is, dx. That adds the extra dimension, which is volume. Okay, so what do you need to know here that's actually important? Well, we can actually set this up as the volume is going to equal the integral from a to b, I'll leave the pi out in front, of our r of x. Our r of x is actually our function, which is going to be e to the negative x. That's going to be squared dx. And this will give us our answer. So let's start plugging in our values. So it's going to be pi integral from, well, what's my bottom bound here? Going from 0 all the way out to infinity, e to the negative 2x dx. So don't worry, we won't have any of these problems in this unit. I just want to kind of show you what the volume stuff looks like, give you a little bit of a head start on that. So what I really care about is we should be able to do our problem from here. And once we are here, we're just going to replace that infinity with a b value. So b is going to go to infinity of pi integral from 0 to b e to the negative 2x dx. We do a bit of a baby u sub here, and we're going to get the antiderivative of that to be 1/2. Pull out the negative, so it would be negative 1/2. So how about negative pi over 2 e to the negative 2x from 0 to b. Do not forget that limit notation. So when I plug this in, I'm going to get negative pi over 2 times e to the negative 2b minus e to the negative 2 times 0. Well, this is e to the negative 2. As we go out to infinity of e to the negative 2, it's an exponential that's negative, so it's a decreasing exponential, so it's going to be a 0. So I'm going to get negative pi over 2 times 0 minus, well, in this case, I'm just going to get a negative, or sorry, just a minus 1. E to the negative 2 times 0 is e to the 0, which is 1. And then negative pi over 2 times negative 1 is just going to be a pi over 2. And there you go. That is how you do a volume problem. Don't worry about the setup so much. Just understand how to go from here to here.